I have known Erik for many years, actually for many decades by now. I think at least, I mean, maybe 33 years or something like that.
Yes, yes.
Yes, and I've always enjoyed talking to him, and I will really appreciate it that he will speak today about his new results about a subject which used to be quite famous in 20th century. Now, 20th century is long time gone, but I mean, both me and Erik are people from 20th century, so we like the problems that were fashionable back then. So please, Erik, go ahead.
Okay, thank you, Jan. Yes, I agree that it's an old-fashioned subject. So, and somehow I stuck to it. So I have some. This meeting is being recorded. I guess I can. Okay, I remove it. So, so yes, I will start my presentation. So, so this is about Inbody Schrödinger operators with long-range potentials, long-range pair potentials. So, so this class of potentials or this class of models include a popular atomic physics model I will discuss later. So it's okay. I need to recall the fashionable subject in the last century as in our field, asymptotic completeness for Inbody systems. So after, well, Siegel-Sofer proved it in, I guess it was 85 for short-range pair potentials, and then several alternative proofs came up, and eventually Jan Dereziński proved asymptotic completeness for systems of particles interacting by a class of long-range potentials, including Coulomb interactions. And all these works, except for a single work by Yafaev in the beginning of the 90s, were entirely time-dependent. And the people in the field know that there are two approaches. There's a time-dependent approach and a stationary approach. So except for Yafaev's work, all proofs were entirely time-dependent. And so, okay, so there was no information about stationary scattering theory left, apparently. But there was one work, is Yafaev, as I mentioned. He managed to come up with a stationary proof that gave some results for in a short range case for pair potentials interacting by short range potentials. That means potentials that have a bigger decay than the Coulomb potential. And my work that I did last year. So there's a preprint on the market that came out in November. So this is about extending Yafaev's result to the long range Inbody case, so that you to get some information of stationary type. So maybe I should, because Jan told me that I should start slowly with some introduction. So I actually have something in mind here. So let's see if we can get it done here. So I would like to write something like this. Okay, so what you can imagine here. So this is a physicist's experiment. So when time is close to minus infinity, you have some some clusters far away that come together when times increases. So maybe this is cluster 1 and this is cluster 2. So what is a cluster? It's just a bunch of particles that quantum mechanically are in a state that is bound. So the internal motion is very simple. It's given by a bound state, and then there's some free kinetic energy describing the intercluster movement. And then so maybe this is this corresponds to some channel, incoming channel alpha. So defined by these two cluster decompositions of the particles, and as well as the bound states describing the internal motion of the clusters. So what happens is, and that's what the physicists measure, is that when t goes to plus infinity, there is a complete split up. So you could have this kind of picture that the C1 is there and C2 is there moving, they separate. This is one scenario you can consider. So the particle really don't split up. They're sitting in the same internal bound states. A different scenario would be, for instance, split up into free. So this is the outgoing channel beta that is described here. So a different setup for would be another outgoing channel beta, that it could be free stable clusters that came out of this experiment. So maybe, so now I can denote them by D1, D2, and so on. These particles here. So this would be another scenario. This is a very beautiful picture, mathematical and as well as speaking in terms of physics. And it's also what you detect in physics. And asymptotic completeness was a statement saying that this is really a true picture, what I have depicted here, what I have done. So this is what happens for any incoming states, that it splits up into configurations of this type, or maybe an infinite sum of states corresponding to the two I have depicted. In the assertion on assertion asymptotic completeness, there's the existence of wave operators as well as their completeness. The existence of wave operator is not as easy as for the one-body problem, because you might face this problem that one of the clusters, for instance, this one, or maybe one of the outgoings, is described by an internal bound state that with energy that happens to be located at a threshold. And then you don't know that the corresponding bound state has a good decay. So for that reason, it's actually a non-trivial problem to show that the wave operators exist. That's completely opposed to the one-body problem. And in particular for atomic physics models that I'm going to discuss in a minute, it may happen that some eigenvalues are sitting at thresholds, and that you don't have a sufficient decay of the bound states to come up with a trivial or sort of easy Cook type of argument for the existence of wave operators. So this was my general introduction. So part of my work is to construct the wave operators by a time-independent way, without using any decay information on cluster-bound states. So let's see. So I erase this. Yeah. I have a couple of theorems the atomic physics model, well-known one. But of course, the nature of the theorems are much more general. And I have some comments. And then I have a possible formula that is natural for the stationary theory. And I have a notion that I have decided this should be stationary complete energies due to one proof of proving asymptotic completeness for the one-body case. But anyway, I'll come back to that. And there is an open problem as related to this, because I'm sort of deriving results that belongs to the stationary theory, but still I have a Enss result on asymptotic completeness as an essential proof for parts of my assertions. So it's not completely stationary what I'm going to present you. So let's see, we go down if I can. Okay. It should, so here it is. So more things coming up. Some asymptotic properties of generalized eigenfunction and how to characterize the scattering matrix in terms of asymptotics of generalized eigenfunction. And then I have a Sommerfeld uniqueness theorem that's essential for my work. And maybe I have time for showing just a tiny thing about the proof. I think so. All my proofs are based on Kato-smoothness bounds, and I had in mind to present a very simple example, but I'm not sure I have time at all. So let's go ahead. First, I would like to recall a few things for the one-body problem. So I need to introduce notation. So there are 3 lines here. So the first line, I have an Hamiltonian 8. So the letters are small. So this is what I have chosen for the one-body problem. Then I turn to capital letters for the in-body situation. So Hamiltonian is the kinetic energy plus a potential that's smooth with a good decay. So it has order x2 minus mu, where mu is bigger than 1/2. So it includes a Coulomb potential. And then small r is the letter for the resolvent for the Hamiltonian 8. So it exists in any complex number. Here it's lambda is real, so lambda plus I epsilon. And what is going on here is that epsilon is taken to 0. And if you take this difference, you get the so-called delta function at lambda that is known from Stone's formula. And I have a standard notation here, the weighted L2 in the third line, weighted L2 space with parameter S. S needs to be taken larger than 1/2 in order to show the existence of this limit, to show the existence of the delta function of H at lambda. So the energy shelf possible identity. This is written this way. So a particular way of writing the non-negative operator, the delta function at lambda, as a gamma star gamma. So really there are 2 ways of doing it, either with plus at both factors or minus at both factors. These are called restricted wave operators and wave matrices at the fixed positive energy lambda. I will define them in a second, in a minute. We'll give one formula for those. They really are connected to the wave operators, and in the short range case, the standard one is this one. You compare the full evolution with the free evolution and take this strong limit of the product. This works. So short range means mu bigger than 1/2. Bigger than 1. So I'm interested in mu bigger than 1/2. So in that case, the dollar wave operators can be constructed. So you have to modify the free energy by some simple d plus minus that depends on momentum and time. So there are 2 terms in the third line. So the time t times the momentum squared, and then there is something that that is not bounded at in an infinity in momentum space, but it doesn't grow as much as psi squared. So it's this integral of the potential along a line. So depending on which time, whether you take time to plus infinity or minus infinity, you get two wave operators, the dollar wave operators. Really, I'm interested in a different modification of the free energy. The symbol is denoted by J. So taking a different one than D, namely J, I get similar wave operators. Now, this J is a solution to the Hamilton-Jacobi equation. I'm not going into details, but this allows me to take the Legendre transform of the function and get some function K that depends on the position X and the energy lambda, and that's a solution to the Eigen equation. And it's a modification of the free one, namely the square root of lambda times the length of X. And here's one way of defining these gamma operators. So, okay, let's just look at the plus thing. So I must admit that so R is used for the length of X, but also for the resolvents that you have that you have in the middle. The resolvent at the energy lambda, but the limit is taken from above. And then there is the first dot. That means that you plug in a nice function. And what you do is that you use spherical coordinates. So then you have a different dot. So it's R times an angle. You may, by taking this limit, you may get something that you get a function that depends on the angle on the unit sphere that I denote by C. So it happens to be a well-defined operator from a weighted L2 space to L2 of the unit sphere. And the gamma minor is similar, but you only have to change sign in the last argument, R2 minus R. I just state these formulas for completeness. And the scattering matrix, that takes incoming scattering information to outgoing scattering information. And one way of defining it, although this is not the standard way, is to define it by this formula in blue. So it's the unique unitary operator that takes gamma minus to gamma plus at energy lambda. Okay, so this is sort of what I want to say about the one-body problem, and these concepts here play a role in my work, although this will not be revealed really today. So let's look at the Inbody model where with Coulomb potentials that is very standard in physics. So you have in particles with a position, mass, and charts X, M, and Q, and you need to separate out the center mass motion, and so you get a D times n minus one dimensional space denoted capital X, and you can decompose X into a sum of a space that's called X super A. That's a subspace of internal motion of the clusters. So A is a cluster decomposition into K cluster C1 and CK. And then with the subscript A, I get a subspace I call subspace of cluster motion. As an internal, what is that called? Maybe there's a good word for that. I don't remember, but it describes the mutual movement of the stable clusters when we are talking about a channel. So we get that these two subspaces span X in an orthogonal way. If you introduce a proper inner product on X, and this is standard notation for how to decompose a vector X into the corresponding components. And then we have the notion of, we have a partial ordering on the class of on a set of cluster decomposition. So we say that B is smaller than A if the corresponding subspace of internal motion is included in the similar one with an A. And there is a notation ij. So this means this is a cluster decomposition in n-1. So you just have lots of singletons, except for one consisting of two particles, namely I and j. And what does it mean that I and j, this n-1 cluster decomposition is smaller than A? It means that the two particles labeled I and j belongs to the same cluster of the cluster decomposition A. So with this in mind, we can define the potentials V super A, that's sum of pair potentials where B is smaller than A, and sub-Hamiltonians H super A. In this way, the part of the kinetic energy square plus this potential just defined, and the subspace is L2 of the X super A, and the full Hamiltonian corresponds to the biggest cluster decomposition A max. So this is this Hilbert space is denoted H. And then a channel alpha is nothing but a triplet. So I need a cluster decomposition A into a finite number of clusters. And then I need something that describes the internal motions. This is a bound state U super alpha and a corresponding energy lambda super alpha. So this bound state is normalized. It's a bound state of the H super A, and lambda alpha is real, of course. This you can do for any cluster decomposition A that's not the biggest one. So this is a channel. And the channels describe, and this is part of the concept of asymptotic completeness, describe the whole scattering picture. So there's the intercluster potential that is a sum of pair potential linking particles belonging to different clusters of A. This is denoted I sub A. So the dollar channel wave operators W, there are two with plus and minus, but these are defined for each channel alpha. And this is parallel to the one-body problem. So you have the full evolution. Now I have a tensor product. So you have this internal bound state U super alpha, and then some modified kinetic energy. It's described in terms of a dollard evolution. So similar to the one-body problem, it's T times C squared, and then some integral of the potential. Now it's the intercluster potential restricted to not to Xi but to Xi sub A. So that means to the subspace X sub A. And you see, it's not Xi squared. It's the intercluster kinetic energy that defines the first term. So Jan Dereziński proved that these exist, these wave operators, and they span the whole continuous spectrum, provided mu, the parameter, is bigger than square root of 3 minus 1. So that includes the mu equal to 1. So the physical model I just introduced. So now stationary theory for this what would it mean? So introduce for each channel K sub alpha, this kinetic energy P sub A squared plus the cluster energy lambda super alpha on this space, and then we diagonalize this operator K alpha by the Fourier transform. It's just the Fourier transform probably translated and scaled. This will indeed diagonalize the operator K alpha, describing the intercluster motion. Okay, the wave operators intertwine K alpha and H. And for that reason, this is completely abstract. You can you can look at the scattering matrix by composing these two wave operators with plus and minus, and then pass to the space where the kinetic energies are diagonalized. This is by these Fourier transforms. Then you get some S hat operator for each pair of channels beta and alpha. So by abstract reason, this operator has a fibered structure. It's a direct integral of some operators over the energy interval. That's the intersection of two intervals. So this is completely abstract, and my interest was to do something better. I would like to know a little about this fiber operator, but it's only defined almost everywhere, and the abstract proof of this assertion doesn't help me anything. So it's only defined almost everywhere. That's something. So can we do a little better? So can it be constructed concretely given if given an energy? Are there some formulas for it concretely? Can it in some sense be considered as a unique quantity? So that would mean some continuity property to get beyond this almost everywhere feature. You should have some continuity property to fix it as a unique quantity. And thirdly, so when is the entire matrix, when I look at this quantity here, is sub beta alpha as just an entry of a scattering matrix, a bigger operator. When is this bigger operator is of lambda a unitary operator? Abstractly, you would have it for this property for almost every energies, but can you characterize when it's actually unitary? And I come up with affirmative assertions to these three problems here. In particular, the first two, as you will see, and also come up with an open problem. So here's the first theorem. So this operator valued is beta alpha. It's not only defined almost everywhere, it's defined everywhere away from a set of thresholds and eigenvalues of the full Hamiltonian as a weakly continuous quantity. So it's uniquely defined. And also, if I put all these interests into a big operator as I did before, and consider the scattering matrix, then this is a weakly continuous contraction. It's defined everywhere. It's a weakly continuous contraction, and away from a null set, it's a strongly continuous unitary operator. The best property I can imagine. But I have this assumption that it's only away from a null set. I would like to get beyond this, but I don't have a clue. A second theorem is about the channel wave matrices. Now I define them all only for the one-body problem, but here's a way of introducing them that also works for the one-body problem. It's different from what I did before, but it works for the Inbody as well. So let's see what comes up. So I have a fixed channel alpha. So this is this triple. And then I have a function f that goes from this interval, from the cluster eigenvalue to infinity. It's a continuous compactly supported, this function f, and it does not, the support does not intersect the set of thresholds and eigenvalues. I let S be a fixed number bigger than 1/2. So then I look at this one, the wave. There are two formulas. So the wave operator corresponding to alpha, not on an arbitrary L2 function phi, were localized in energy by this function f. This is what's to the left of the formula. It's an integral of a function that's fairly explicit. So I have f of lambda, that's explicit. Then I have the Fourier transform f sub alpha phi. restricted to lambda. That's explicit. And but then I have the wave matrix, gamma, let's say minus. If I decide that we look at the minus version, so gamma minus sub alpha. This is and the adjoint. So this is the wave matrix at energy lambda. And the assertion is here that this operator exists so that the formula 2 is valid, and this operator goes from L2 to a weighted L2 space, L2 of the sphere a unit sphere to a weighted L2 space described by this S that's bigger than 1/2. So this is uniquely. So this is strongly continuous in lambda. This wave matrix. This is an assertion. So this is a way of uniquely defining the wave matrix gamma minus sub alpha. So in particular, if phi happens to be in a good weighted space, actually with the same parameter S is bigger than 1/2, then it's well known that the restriction of the Fourier transform is well defined and continuous. So the integrand in this case is actually a continuous compactly supported function with values in some big weighted L2 space. But in general, you need different interpretation of the integrand. So anyway, that's the two main theorems. So I have comments to this theorem. So one could choose f of lambda, this function compactly supported away from Fresch's and eigenvalues, to be e2 minus it lambda times a fixed time-independent function. And then by the intertwining property, the formula simply spits out a wave packet in time, right? So to the left, you have the evolution of this particular state. And this is, as the formula says, that it has this formula. So the full evolution is going to just a complex exponential. So just from the definition of the wave operator W super minus sub alpha, we know the evolution of the left-hand side of this wave packet when t goes to infinity. The question that the physicist would like to know is how does the wave packet look like when t goes to plus infinity? So if you look at the formula here, so then it amounts to looking at the asymptotics of the functions in the range of the wave matrices. And I have some formulas. I'm not going to present them, but the asymptotics are given in terms of the boundary value of the full Hamiltonian from above, and this is a rather complicated quantity. How I do, let me just reveal that I deal with this complicated quantity by a series of estimates that are all of the Kato type. So I use Kato-smoothness bounds. And if I go further on, is there a way of solving this problem for the physicist? So how does the right-hand side, this integral, looks like when t goes to plus infinity? Well, you could use this formula here, form. So the minus wave matrix is linked to the plus wave matrices by this formula. So here you can see that the scattering interest of the scattering matrix actually enter into the formula. So the outcome of this, if you plug it in, and if you have a plus instead of minus, then you know the asymptotics of the integral when t goes to plus infinity. So the outcome is what you sort of expected, that all scattering information is encoded into the entrance of the scattering matrix at fixed energy. But actually, I do have some assertion about the asymptotics of functions in the range of these scattering wave matrices. So let me see if I have time to come back to it. So, but the next subject is a possible formula So this is the point where I sort of take the asymptotic completeness proven by time-dependent methods, and that's all we have that's on the market. Well, I implement this in this way. So from the formula to the second theorem, I can get this, that if I take the restricted wave operator corresponding to a channel beta, restricted to lambda, apply it to a fixed vector psi from a nice subspace of Hilbert space, and then I take the norm squared and sum over all cluster energies lambda super beta smaller than the energy lambda that in question. If I take this entire sum, I get something that is estimated by the expectation of the spectral density, the delta function at lambda. So this is something you can get out of this as asymptotic. This is actually only orthogonality of channels that are used for this assertion. But if I add asymptotic completeness, I actually get equality, but unfortunately not for all energies, but away from a null set, n sub 0. So then this is possible, this formula. Maybe the other one should be called Bessel. I mean, those that know Fourier series. I mean, all of us do. But
excuse me.
Yeah.
Do you know? Can you characterize this n0? So these are thresholds, presumably, but
no. It's they are not. Lambda is not an eigenvalue of threshold. So I'm away from that set. But then there still might be a Lebesgue null set for which I in 5a have a strict inequality, not equality between these forms.
Does it have some physical meaning? I mean, what would be the mechanism for that?
I don't believe it. This is I don't believe that this is that there's a strict inequality. I think that the Parseval is correct. It's just beyond my what's called. I cannot prove it, right? I will.
Okay. Thank you.
I would like to. So that's why I will pose it as an open problem. So the formula here is valid for psi in a dense set nu, and I'm not going to be precise about that, but what I need actually for proofs. I'm not giving proofs, but it's definitely true for this nu, it being the weighted L2 space I considered before. So, but then given this assertion 5b, I come up with a notion of completeness. So a fixed energy that's not an eigenvalue nor a threshold. This I call a stationary complete. If I take this, let's say, in the intersection of all weighted L2 space, look at the two forms on this subspace, namely the left and right hand side from the previous formula. So if it happens that these are equal, the two forms are equal, not only that the first is smaller than the other that I know, but that are really equal, then I call lambda a stationary complete. And as the content of 5b is that I only know it away from a null set. But so the question here is the open problem. So are all energies stationary complete? That's a relevant question. And actually, this is not an easy problem. As I mean, of course, I have worried a little about this, and I've not been good at citing other people. But I should mention that Isusaki actually published 2 or 3 papers related to this. So he did prove something like this. He did prove it more precisely for the free body problem. If the pair potential, if the pair potentials decay faster than R2 minus 6. Okay, so R2 minus 6, after all, there's a gap up to Coulomb potential. So, and his proof is absolutely very complicated in one of his papers 20 years back. So this is even in a case where suppose there's only the free channel, there's only one channel for a system with long range potential. It's a non-trivial assertion, but it should be true. It should hold. Okay, so at any such energy, any stationary complete entities, for that I have the nice property of the scattering matrix that I mentioned, that it's a unitary at all energy and strongly continuous at such an energy. So that's the ingredient that I need for the stronger and natural assertion about the scattering matrix. But I don't know a proof. And you see the subtlety here. So I know that it's a sum of factors. Suppose the sum is finite. Why? I mean, I know it's correct or almost everywhere, this formula. So why not just use the continuity? Then I'm fine. The right-hand side is continuous, no problem. But okay, the adjoint thing, this is strongly continuous. That I have already asserted in a theorem. The first factor, well, the adjoint of something that's strongly continuous is not necessarily strongly continuous. That's very unfortunate, right? Because otherwise I would have two strongly continuous operators that is going to be strongly continuous. So it's just not working. That's open. But what can I do? Suppose I have an energy for which I know is stationary complete. Well, then I have various theorems I can present for you, and I plan to. So please help me with time, because I forgot my watch this morning. So when it's up, so please tell me. So one thing I wanted to do, instead of dollar, I wanted to go to the Hamilton Jacobi setting that I mentioned, indicated first. So you have this intercluster potential for cluster decomposition B, I denoted by I sub B. So it has a singularity near collision planes when clusters in configuration space are very close. So one way of avoiding this problem, I would like to construct a one-body potential, is to make a cutoff of logarithmic type near collision planes, and then you get a one-body potential with decay in all directions. And corresponding to this one-body operator, I look at the Hamilton Jacobi quantity in momentum and time, and consider a one-body wave operator. And then I can ask what is the difference between using this Hamilton Jacobi equation and the dollar I mentioned before. Well, the answer is very simple. The two wave operators are linked by some explicit oscillatory factor e to I theta, where theta is momentum depending. And this factor has some nice continuity property. So if you can prove some continuity property for one operator, say the Hamilton Jacobi quantity, then you have it for the dollar and vice versa. But I prefer this one. And so now you can, as I mentioned, the wave operators, it's not easy to prove that they exist. There's no Cook theorem that's easy here. So one thing you can do is that you can realize that instead of all this modification, you can put in as a modifier the one body wave operator, this W brief sitting there in the red column. And you can now this an extra factor that's time independent, phi, phi sub alpha. That could be 1. That's fine. Then you get the same quantity as 2 lines above. But you can actually choose this phi. I call it a stationary channel modifier in such a way that it's localized for the plus case in the outgoing region in the phase space, and for the minus case when t goes to minus infinity in the incoming region. So that's a good thing for my constructions. That's what I do, but I don't have time for going further into the proof. But this is the first thing that I cook up some good stationary channel modifier for which I can prove, actually independent of Jens' result, that this limit exists. And then the next thing is to prove formulas for the guy. So I'd like to discuss, so what is the time, Jan?
It's still at least 15 minutes.
Oh, 15 minutes. Okay, so then then I can do most of what I have here. So I would like to discuss the asymptotics of various generalized eigenfunctions. That as I announced previously, it turns out that the right spaces to work with are Bezo spaces, so here is the definition. But let's forget about how it's defined. I mean, it's certain decomposition of the configuration space and some well, various constructions. But what is really what is really important is that the Bezo spaces and weighted L2 spaces are nested. So I have in the middle the configuration space, the Hilbert space H, L2 of the X, and then I have a weighted L2 spaces. So we know that for the limiting absorption principle, L2 S, where S is bigger than 1/2, is important. So S is bigger than 1/2. So to the far left, I have L2 of S. For that, as you can apply the resolvent to a vector in this space and end up with something to the far right, L2 of minus S. And in this topology between these two weighted L2 spaces, you actually can show that the resolvent has a limit from above. This well, why do I write this? Also from below, so I need a minus, but there are two assertions. So this is the limiting absorption you have for if you consider a resolvent in this weaker topology than the Hilbert space topology. So of course, in stationary scattering theory, the limiting absorption principle is very important. But back to the Bezo spaces. So these are some spaces that are slightly bigger than better than L2S, where S is bigger than 1/2. So you can see the Bezo space is bigger, but still smaller than L2 1/2. So it's sitting just at the borderline for having the limiting absorption, and similar for the adjoint B star. And it turns out that you can consider resolving. This is the best, the optimal limiting absorption in the strong weak star topology as an operator from B to B star, and you can take the limit in this topology. This is the strongest assertion of statement of limiting absorption principle. And then maybe I should mention that with the subscript 0, you get a strictly smaller subspace than the B star. So it's in some norm you have it's some smallness at infinity in configuration space. But I don't think I will explain you the correct all this mess up there. So, but this is standard. So the limiting absorption principle, the strongest one, The strongest version is at the bottom of the slide, and this is what I'm going to use. That's the way I interpret this lambda plus I0, this operator, this limiting operator as, okay. So now we have some characterization of the wave matrices. So gamma plus minus, these were the restricted wave operators, right? So for each channel, you have such a thing. And you have a Hilbert space G that's a direct sum of L2 spaces of spheres. And that, of course, is a Hilbert space. And now there is a class of generalized eigenfunctions that I call the minimum class, and for good reasons. So it's the fixed energy lambda, non-threshold energy lambda. It's a set of functions in phi in B star. So they're sitting outside the Hilbert space that are solutions to the Schrödinger equation at the energy lambda in distribution sense. So this is a set of generalized eigenfunctions, and it's the minimum class, because if you have a smaller one that's smaller than in B star, then it's actually zero, identical zero. This is a theorem. So of course the delta, if you apply the delta operator, the spectral density, if you like, at the energy lambda to any psi in the Bezier space, then you end up with a generalized eigenfunction in this space, this space B star. Okay, so if lambda is stationary complete, I have defined it for you. Then you can actually characterize the space E lambda. So here is the theorem. So if lambda is stationary complete, there are various operators, 3 of those, right? So you have the restricted wave operator that goes from B to G. You have the wave matrix gamma star that goes from G to the space of a minimum generalized eigenfunction, and you have the delta function that goes from B to the same space E sub lambda. They are all mapping onto. And besides the wave matrices gamma star that goes from G to E sub lambda, it is a bijective. There are two of those, but they're both bijective and bicontinuous. So it's a parameterization of what we have gotten here is a parameterization of the class of minimum generalized eigenfunctions by G, this direct sum of L2 spaces. This is one theorem, one general theorem about these gamma operators. And now we come to the physicists' experiments, right? So there's some alpha incoming scattering experiments, and the physicist would like to know what happens when t goes to plus infinity. So he would like to know, or she would like to know the asymptotics of functions in the range of the wave matrix gamma minus star. Okay, so here is an answer. So we look at a one-body potential with we breathe. So remember that I have this intercluster potential IB, I sub B. Then I made some logarithmic cutoff to make it a one-body, and this is exactly what is here, one-body potential. And corresponding to this, not only you have a solution to the Hamilton-Jacobi equation, you also have a solution to the Eigen equation by a Legendre transform. So a function k that depends on x sub b and the energy lambda, solving the Eigen equation at infinity. So corresponding to this k, you have a family of quasimodes. So for any g in L2 of the sphere, you have this function in x sub b. So forget about some energy factor here. So what is important is you have some Jacobian, that is the length of x to some power, some Jacobian, and then you have an oscillation by the solution to the Eigen equation k sub b, an oscillatory factor. So when you in a plus case you have an outgoing spherical wave. That's what you can read here. And then the momentum depending momentum depending is sitting in D at this point on the unit sphere plus minus x sub b normalized. So this is a quasi-mode. So the theorem is that if lambda is any stationary complete energy, alpha is any channel with a channel energy smaller than lambda, then the following existence and uniqueness results hold for any G in L2 of the unit sphere. So here's the existent part. So look at the reddish stuff. So define phi to be the wave wave matrix at the incoming wave matrix gamma minus star applied to G. This is phi. And then I define some function d sub beta for each beta with energy lambda beta less than lambda. Lambda not should be lambda, sorry. But so d beta is nothing but this scattering, this part of the scattering matrix applied to G. And if I stick that into the formula in blue, so remember G is fixed, so the first term is defined. I have defined phi, the left-hand side, by the first red equation, and the infinite sum or finite sum or whatever on the second term is defined in terms of G sub beta. That's defined by the second equation in red. So this is an assertion about the asymptotics of any function in the range of the incoming wave matrix at lambda. And by the way, I mean, the way you defined it, the sum, it might be an infinite sum, is in the quotient norm in B star across, or divided by B, by the smaller tuple of space. And the second statement is a converse. So if now you have to read the red thing first. So if this formula 7 is correct, remember G is fixed, and now the formula is correct for some phi that's in this space E sub alpha, and for some sequence D sub beta in the Hilbert space G. If this is the case, that you have the formula 7 for some vectors like that, then you have the conclusion that phi is given exactly, the left-hand side is given exactly as in the first statement. So phi is nothing but the wave matrix applied to G, and these G's, the components of this vector in the Hilbert space G are given by in terms of entrance of the scattering matrix as in the first statement. So it's an existence and uniqueness assertion on the asymptotics of any generalized eigenfunction in this space, corresponding to the experience where you have an incoming alpha configuration. So this was something that you can prove. So by the way, there is something that I was always a little puzzled about. So the limiting absorption really goes back to Moore, in my opinion. So that's in the around 80, that he could show a limiting absorption for a free body system, and then this was extended. So since then it was known that the resolvent has a limit in between weighted L2 spaces, but what is the asymptotics of functions in the range of this limiting resolvent? This was not, I never saw this before, except for the Isozaki paper I mentioned before on the very special conditions. So there is a separate assertion here that I think has some interest. So this is the next corollary. So let's take lambda such that we know that this Parseval identity, so it's stationary complete. Take a psi in the Bezier space, then the resolvent, how does it look like? The limiting of resolvent applied to psi. Well, it's given by this infinite sum. So this is really the top order asymptotics. So it is an identity in B star mod B star 0. And the quasi-modes from before are used in this formula. And the definition of the G functions, the components of the vector G, is this one in red. So they're defined by the restricted gamma operator. And then the sum of all beta. So you have such an assertion, the asymptotics of the functions in this range is specified, and vice versa. So if you have such a formula, then the data to the right is given as in the assertion 1. So,
Erik, you should wind up in a few minutes.
Yeah, that's fine. Thank you. So the sum, okay, so these corollaries I have mentioned, these are can be seen as consequences of a maximal optimal version of the so-called Sommerfeld uniqueness result. And I think Isozaki was the first that came up with this such a Sommerfeld uniqueness result, although in a weaker version. And this is 30 years old, this result. And this could be, I don't have time to explain you what Sommerfeld uniqueness is about, but maybe in just in a few words. So you don't have a good notion of radiation conditions for the Inbody resolvent, because the resolvent is simply too complicated. But there is some substitute that we call Sommerfeld uniqueness. So this is intercluster radiation conditions in some sense. I don't have time to explain it. So, but my very last slide here is that I wanted to show you what a Kato, how you get a Kato bound. That's really behind all I have been saying. I have many Kato-smoothness bounds. So let's look at Yafaev's simple observable. So it's a one-body Hamiltonian, a potential of usual type, and you like to have establish a non-trivial bound, a Kato-smoothness bound. So what do? You look at an observable, some bounded operator, this psi. You compute the commutator and show that to top order this has a sign. So in this case, the Hessian of this modification of R is definitely has a sign. It's a projection up to a factor. So it can be factorized as Q star Q. So now we have the projection, then with a different scaling in front. This is my Q. And then if you integrate on a proper state, full evolution, you get this time bound. This is a Kato-smoothness bound. And in his theory, very famous theory that goes back a long time, this is shown to be equivalent to many other assertions, but in particular, you can, if you sandwich the delta function at lambda by Q and Q star in this way, you have a bounded operator. So all my formulas for the scattering matrix, and for instance, they are given in terms of such a quantity that you have in the last line. But I don't have time. So my time is up.
So thank you.
Thank you.
Questions or remarks? So I have actually several questions, but okay, well, one question. At which point do you need Biesov spaces? Do you need them to prove the stationary the existence of stationary wave operators, or you need them only in your analysis of generalized eigenfunctions after assuming stationary completeness?
Yes, I only need them for the asymptotics that I stated. For instance, this one, this is clearly stated in terms of B star, right? So if I don't use, if I didn't know B star, the Bezo spaces, I would not know what to write. Okay. I had no idea what the assertion should be, and similar for the other corollary, no idea. And also the previous results relies on this theorem. I mean, it's absolutely essential that you deal with Bezo and B star spaces. Otherwise, there's no characterization. Yeah, but if you don't impose a station, so could you remind the definition of stationary complete? Yeah. So this is 5C here. So I have a certain nice subspace of the Hilbert space here, the intersection. I mean, it's chosen partially random, but it could be C0 infinity if you like. So on this form domain, you have two forms. Then the two on the both sides of the identity, and the lambda is complete if these two forms agree. Yeah. Okay. So you mentioned that this would be a remaining open problem to prove this for all energies outside of thresholds and bound states, right? Yes, that's if we can go one step back. So here was the first theorem I presented, that S beta alpha is weakly continuous. Of course, you would like this to be strongly continuous. And here in the second statement, that away from a null set, the whole matrix is strongly continuous, a strongly continuous unitary operator. And then I can add that if lambda is not or is stationary complete, this is the case almost everywhere, then you indeed have the second stronger assertion that the scattering matrix is strongly continuous at this energy and unitary as well. So the property is relevant for this theorem. And if someone can come up with a good resolvent formulas or something, then maybe it's possible to prove that any energy is stationary complete. But I don't know personally. Maybe there are some other questions from the audience. I still have some questions. So there were operators capital Phi. Yeah. So I call them modifier. Yeah. So are they kind of Isozaki-Kitada modifiers? No, not at all. I mean, their modifier is in terms of some phase that solve phase functions that define that solve the eigenel equation, right? This is in their theory, but they're nothing like that here. It's a product of phase space localization operators. So typically first order in momentum. But also, yeah, there is that's a structure what I need. Okay. So are they simple operators or are they complicated operators? They're very simple. So it's they are functions of first order operators. So that means a first order in momentum, right? And then so it's P dot some vector field, right? This kind of thing. So this vector field is bounded. This will amount to some relative bounded operator, and the phi is in terms defined as products of functions of such first order operators.
Yeah, so they are kind of well, phase space localizations.
Yeah.
But can you drop them, or they are necessary?
I actually really do need them. So it's a complicated construction, and the reason for that is that I don't use any fall off of U super alpha, right? It's just an L2 function.
Mm-hmm.
So how if you want to use the Cook criterion, you have a severe problem when you don't use cut off or a property of U sub alpha, U super alpha. So then you need to localize to some good regions in phase space. So it's really what I use is functional analysis, not pseudo differential operators.
Mm-hmm. Yeah, sure.
It's a minor thing, exactly as you did yourself, right? In your proof of asymptotic completeness. But your modifier, your stationary modifier is time dependent.
Mm-hmm.
That's a difference. But otherwise, it says a similar structure.
Okay. And what would you formulate as interesting open problems that still remain? I mean, well, you mentioned this stationary completeness, but what else?
When so of course, regarding regularity, you cannot hope for more. Where did I have it? It was up here. So strong continuity. I actually think that the Yafaev has a counter example. I mean, you cannot hope for continuity in uniform norm, operator norm. So this would be the ultimate solution: a strong continuity of the scattering matrix. That's mm-hmm. what you expect. And then of course you would like to know how it looks like. And then it's much more subtle, right? Does it have a nice kernel, and where are the singularities, and so on? So this is my issue was just to see if one could construct them. I mean, because there's no theory on the market of this type, as far as I know. So yeah, we have asymptotic completeness. That's fine, but what about this almost everywhere defined scattering matrix? That one should be able to say something about this. This is what I did.
Thank you.
Can I answer a question? Can I ask a question?
Ira?
Yeah. Can I ask a question?
Yes, sure.
What is known about the momentum space scattering amplitudes for the long range case?
Well, I don't think that anything is known unless you use some decay property of the cluster bound states. Because you cannot define it. I mean, of course, in physics literature, there are many papers on scattering amplitudes and so on. But if you use some fall off of your what I call U super alpha, then you can define wave operators and amplitudes and so on. But if you start to think about it, you don't know any decay of cluster eigenstates, then you know nothing. I mean, not to my mind. About
yeah, but even in the one-body Coulomb case, it's even complicated, right? There's no
yes,
delta function there.
Yeah, so it's a complicated singularity. I mean, but in that case, you don't have the bound state problem, right? So it's
right.
Complicated for other reasons.
That's right.
So the diagonal, it's not just a delta function at the diagonal, it's something more complicated. So 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 probably one can say something. I don't know. I did not follow the literature, but if you have a decay of the cluster bound states for Coulomb potentials, then one should have something similar, more detailed information about the scattering amplitude. The physicists should worry about this. I bet that you can find that in the physics literature.
So, any more questions? If not, let's thank the speaker again for a very beautiful talk.
Oh, thank you. Thank you. Thank you for the invitation. So.